Good afternoon, ladies and gentlemen. Can everyone hear me? Awesome. How is everyone doing today? That's awesome. Glad you guys are doing well. I'm also doing well, thank you. So last week we ended off with nebulas. And interstellar dust. So for today, we need to start with how does stars actually form in these molecular clouds? But before we start with that, does anyone have questions on the previous work? You say I can't hear you. Can you hear me better now? Just looking at my settings. Yes, my mic is active. Just want to check, can everybody hear me clearly? Okay, cool. So just the thing, next week, Monday, we are writing our semester test. I just have to check again what the venue is. I think we can probably quickly check to see what the venue is. Let me just go to module lookup. And you can just make sure timetable, module lookup. Come on. Okay, just see. Search. Okay, I can't see to find it now. Exams, semester tests. Okay, I can't seem to find it now, but I will make an announcement of the venue and time we write next week. So for this lecture, we still need to discuss the star births and molecular clouds. So the semester test will be up until what we do today. So where we stop today, till that point is what will be needed to cover for the semester test. Are you guys happy with that? Awesome. So spectra of the interstellar medium showed that its chemical composition is basically the same as the rest of the stars. And by observing at far infrared and radio wavelengths to which interstellar dust is nearly transparent, astronomers can peer inside even dense molecular clouds and find evidence that stars are forming there. In fact, the largest molecular clouds are each massive enough to make thousands of new stars. Nevertheless, such a cloud can form into stars only if small portions of the cloud can be compressed somehow to high density and high temperature. And at least 4 factors resist the compression of an interstellar gas cloud. And those factors must be overcome by gravity before star formation can begin. So remember the key aspects of star formation is we need, where's my pen? So we need to firstly compress the gas cloud for star formation to happen. And for that compression to happen, we need high density and high temperatures. So the 4 factors that we need to overcome is firstly the thermal energy in a gas appears as motion of the atoms and molecules. This thermal motion would make the cloud come apart if gravity were too weak to hold it together. Secondly, the interstellar medium is filled with magnetic fields. Ionized atoms having an electric charge cannot move freely through a magnetic field. So although the gas and molecular cloud is mostly neutral and some ions are included, and that means a magnetic field can exert a force on the gas as a whole, and gravity must overcome the interstellar magnetic field to make the gas contract. So gravity needs to overcome these 4 factors. So the first one is gravity must overcome thermal energy. And then secondly, it must overcome magnetic fields. Thirdly, everything in the universe rotates, and as the gas clouds begin to contract, it spins more rapidly. So think about this as the conservation of angular momentum. So a figure skater with her arms extended will spin more slowly, and if she pulls in her arm, she will spin more rapidly. So just as ice skaters spin faster as they pull in their arms, so this rotation becomes so rapid that it resists further contraction of the cloud. So the third thing is gravity must overcome the resistance due to the rapidly spinning cloud. Then fourthly, turbulence in interstellar medium can prevent a cloud from contracting. And many nebulae are observed to be distorted and twisted by strong turbulent currents that can prevent a cloud from contracting. So the fourth thing gravity needs to overcome is turbulence. So given these 4 resisting factors, it may seem surprising that any molecular clouds can contract at all. But both theory and observation suggest that such clouds can be triggered to form stars by effects such as passing shock wave, sometimes just called a shock. So the astronomical equivalent of a sonic boom. So during such a triggering event, some regions of the large cloud can be compressed to such high densities that the resisting factors can no longer effectively oppose gravity, and star formation begins. So here we have our molecular cloud with an incoming shock wave. So the shock waves moves through this molecular cloud, and that triggers the motion in the cloud, and that continues that motion in the cloud to continue after the shock wave has passed. So the densest parts of the cloud become gravitationally unstable, and therefore contraction starts to happening inside this cloud, and that contraction is then triggering star formation and star bursts. So you guys happy with how a shock wave triggers star formation? Awesome, because everything we are now going to learn forms on top of the shock wave. So no. So the short version of this is we have a molecular cloud. Then we have a shock wave going through the cloud. So what we will learn later on this chapter The shock wave is usually due to a supernova explosion that happened, and then that shock waves moves through the vicinity. It moves through the molecular cloud, and as soon as it moves through the molecular cloud, it causes gravity to overcome these four previous factors we just talked about. And once those four factors is overcome, that means the cloud can start contracting, and that causes new stars to form. Does that answer the question better? Awesome. So shock waves that can trigger star formation are common in the interstellar medium. For example, gas flows of several sorts produce shocks when they push into colder, denser interstellar matter. The ignition of very hot stars ionizes nearby gas and causes it to flow rapidly away, and new stars of all types seems to emit strong winds and jets while they are forming. Supernova explosions create powerful shock waves that rush through the interstellar medium. So in this image, we can see in image A, the nebula is a bubble of intensely hot gas about 70 light years in diameter. It was produced over the last million years as hot gas, and radiation flowed away from massive hot stars near the center of the bubble. Then image B. Millions of years ago, a massive star exploded as a supernova in the top upper left quarter of the image. And hot gas from that explosion is now pushing into cooler gas and causing the condensation of dust, which radiates strongly in infrared wavelengths. So before a star is born and formed, it first starts off as a protostar. So now we need to discuss what a protostar is. So you can understand how low-density clouds of interstellar gas might contract to become as dense as a star. But how does the cold gas become hot enough to be a star? And the answer once again is gravity. To see how gravity can heat a gas, shift your attention to one dense cloud core destined to become a single star. Once that small cloud of gas begins to contract, gravity causes the atoms to fall towards the center, gaining speed as they go. And astronomers refer to this early stage in the formation of a star as free fall collapse. By the time the atoms have fallen most of the way to the center of the cloud, they are traveling rapidly. The atoms begin to collide with one another and convert their inward motion to jumbled random motion of thermal energy, causing the temperature of the gas to increase. When the contracting core becomes hot enough, it produces short wavelength radiation to which the core is not transparent. Then the core's thermal energy can no longer escape, and it enters a new stage of slow rather than free fall contraction. Although the term is used rather loosely by astronomers, a protostar can be defined as a stellar mass object that is compressed and hot enough to be opaque to radiation. It is emitting internally, but not yet compressed and hot enough to be able to generate energy by nuclear fusion, as would a main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to the protostar, plus slow contraction of the protostar itself. And the protostar continues growing deep inside a surrounding cloud of cold, dusty gas. And those enveloping clouds have been called cocoons because they hide the forming protostar from view. So in this image is the HR diagram. And in this HR diagram has been extended to very low temperatures to show schematically the contraction of a dim cool protostar. So in image B, protostars are normally invisible at visual wavelengths because they are cool objects and are deep inside dusty clouds of gas which blocks visible light. But they are detectable at infrared wavelengths. So here we will see a protostar being formed, and as it's being formed, it will gain more higher temperatures and its luminosity will rise up. And then at a point, it will blow away once it starts with nuclear fusion, its cocoon and outer layers, and it will start its life on the main sequence. Protostars are not easy to observe. Astronomers calculate that a protostar stage is less than 1% of the lifetime of a star like the Sun. And although that's a long time in human years, you cannot expect to catch many stars in a protostar stage. Furthermore, protostars form deep inside clouds of dusty gas that block your view at visible wavelengths. And being cooler than full-fledged stars, they produce radiation primarily at longer wavelengths. Astronomers must therefore depend on observations at infrared and radio wavelengths to search for protostars in their natural environment. So add my favorite object to observe, the Orion Nebula, also known as Messier Object 42. Something interesting. Side note, are you guys familiar with Messier Object? Okay, so just this is an interesting side note. So the French astronomer Charles Messier created a catalogue of objects he could observe with his telescope, and that was in the mid-1700s, so the 1750s to the 1770s. And he wrote up all the phenomenon objects in space he could see with his telescope, and he called them Messier objects. So in his catalogs, there is 110 astronomical objects. And these are deep sky objects, nebulas, planets, comets. So before we have our standard classification of objects now, there was a few. So the Messier catalog or Messier objects was one of them. But each year, there's a competition called the Messier competition, where people around the world need to see if they can see all 110 Messier objects in one night. And then they have to prove that they have observed it. So take a photo of the object through the telescope and timestamp their location and time. But what makes this quite difficult is it's 110 objects in one night, which is an extremely lot of objects. So your timing has to be perfect. And the other thing is, some of them you can only see at certain times. So some of them just before sunset, some of them just after sunset, for example. And if you miss one of the objects, that means you're wasting time to find it. And then you won't be able to see all 110 objects in one night. And then you have to restart your observation. So that is a fun challenge every year. So that is just something you can read up about if you're interested in. But the Orion Nebula is known as Messier Object 42. And inside it lie four brilliant blue, white O and B stars known as the trapezium of the nebula. The most luminous in a cluster of a few hundred stars. Surrounding those stars are glowing filaments of nebula more than 8 parsecs, so 26 light years across. Like a great thundercloud illuminated from within, the churning currents of gas and dust suggest immense power. The significance of the Orion Nebula lies hidden, figuratively and literally, beyond the visible nebula, and this region is ripe with star formation. So note 4 important points. The visible nebula is only a small part of a vast dusty molecular cloud. You see the nebula because the larger stars born within it have ionized the gas and driven it outward, breaking out of the molecular cloud. Visual and infrared observations reveal small dusty clouds of gas called Bok globules that may be in the process of forming stars. And secondly, a single very hot and short-lived O star, one of the stars in the trapezium cluster, is almost entirely responsible for producing the ultraviolet photons that ionize the gas and make the nebula glow. The star is so massive that it has already become a main sequence star, while its smaller siblings are still protostars. Three, infrared observations reveal clear evidence of active star formation deeper in the molecular cloud behind the visible nebula. And then fourthly, many of the young stars in the Orion Nebula are surrounded by disks of gas and dust. But one thing that we will also learn is star formation is contagious. So not only can astronomers locate evidence of star formation, but I also have found evidence that star formation can stimulate more star formation. If a gas cloud produces massive stars, those massive stars ionize the gas nearby and drive it away. When the intense radiation and hot gas pushes into surrounding gas, it can compress the gas and trigger more star formation. Like a bushfire moving through the interstellar medium, star formation can spread itself, especially by the actions of massive stars. And astronomers have located signs of such episodes. So in this image, we can see the star-forming region in 11b. So in image A, the blast of light and ultraviolet radiation from the formation of an earlier generation of stars compressed neighboring gas clouds and triggered the formation of the stars at the left side of the frame. Those stars are now triggering the birth of a third generation of stars at the right. Note the Bok globule at upper right. And then in image B, compression can trigger the formation of very massive star clusters. Superstar clusters Westerlund 1 contains approximately 500,000 stars, and some extremely massive. It must have formed no more than 5 million years ago. And what this tells us, the stars over here, these O and B type stars, when they form, they pushed away the gas in this region. That started compression over here, and that compression now is starting the formation of new stars. Here we can see the Bok globule. And usually when such an event happens is we can get a star cluster. In what makes a star cluster quite interesting, and we'll talk about it in a later lecture, is that are stars that formed at exact same time. So clusters is a very good place if you want to study different stars and stellar evolution, because those stars formed at the same time. And those stars starts to differ, so meaning in color, in brightness, in temperature. That means each one of those stars is going through a different evolutionary stage. So that is one way we can study how stars goes through its life cycles, by studying these clusters. So the history of star formation in the constellation of Orion is written in the stars itself. Judging from the luminosities, estimates, masses of the most prominent examples, the stars at Orion's west shoulder are less than 12 million years old, while the stars of Orion's belt are almost 8 million years old. And the stars of the trapezium at the center of the Great Nebula are no older than 2 million years. Star formation has swept across Orion northwest to southeast, apparently beginning near Orion's west shoulder. The massive stars that formed there probably triggered the formation of the stars in Orion's belt, and the star formation episode may then have caused the formation of new stars you see today in the Great Nebula. So here we can see the hot trapezium stars. This is the direction to Earth, and this is the expanding ionized gas. And that caused protostars to form in the molecular cloud. So when most of the material in a protostar's cocoon has fallen inward or been driven away, the protostar will no longer be quite so hidden, and the locations in the HR diagram of protostars that have become detectable at visible wavelengths because their cocoons have disappeared is called the birth line. Once a star crosses the birth line and becomes visible, it continues to contract and move towards the main sequence at a pace that depends on its mass. Stars in this late stage of formation are sometimes called young stellar objects, or YSOs, or another term for this pre-main sequence stars, to distinguish them from earlier protostellar stages. The more massive a star, the stronger its gravity, and therefore the more rapid will be its contraction. The astronomers calculate that the Sun took about 30 million years from when its cloud began contracting until it became a main sequence star. But a 30 solar mass star would take about 30,000 years, and a 0.2 solar mass star needs as much as a billion years to finish forming and reach the main sequence. So this is quite an important point, which means the more massive a star is, the quickly it will go through the stage and end up and start its life on a main sequence. The smaller it is, the longer it will take. As a contracting molecular cloud core becomes a protostar, the cloud rotates faster and faster. The rapidly spinning core of the cloud must flatten into a spinning disk like a blob of pizza dough, spun into the air. Gas from the envelope that has lost some of its orbital velocity through collisions can sink directly to the center of the cloud, where the protostar grows more massive. Surrounded by the disk, other infalling material can add to the disk and then move within the disk plane towards the star. So in this image, we can see the more massive protostar is, the faster it contracts. A one solar mass requires 30 million years to reach the main sequence. The dashed line is the birth line, where contracting protostars first become visible as they dissipate their surrounding clouds of gas and dust. Compare with figure 9.8, which shows the evolution of a protostar of about one solar mass, as dashed line up to birth line and a solid line from birth line to the main sequence. So to put this into perspective, we have our through the gas cloud. That's what we call the triggering of the gas cloud. It starts with its contraction. So due to that shock wave, the gas cloud now becomes to rotate, and that rotation starts more contraction. Then conservation of angular momentum spins the cloud, and that flattens the cloud from the top and the bottom. And then with the angular momentum increasing into a growing protostar at the center of the rotating disks of gas and dust. You guys happy with the explanation of how a protostar forms? Awesome. So while we are learning from these young objects and protostellar disks, we need to learn 3 new terms. So question, so does the gravity cause the angular momentum to increase? Yes, that is correct. So star formation regions contain types of stars so young they must have formed recently. We call them T Tauri stars. For example, are understood to relatively low mass protostars ranging from 0.5 to 2 solar masses, still in a slowly contracting pre-main sequence phase. And infrared observations reveal the complicated shapes of star-forming clouds that are strongly affected by radiations and winds from nearby massive luminous stars. And the formation of massive stars may both foster and disturb the formation of the lower mass siblings. So what causes the process to start? So the process can one usually of 2 main reasons. The one could be a supernova explosion that causes a shock wave to move through the gas cloud, and that triggers it. And the other one is if you have massive stars that is nearby, and they start their life on a main sequence. That means they need to push away the outer layer, so they are cocoons. And by pushing that gas away and outward, causes a shock wave into the surrounding gas, which triggers more stars to start to form. Does that answer your question? Awesome. So in the HR diagram, newborn stars lie between the birth line and the main sequence, with just the properties you would expect of stars that have recently lost their dust cocoons. Young stars tend to have very active hot corona and chromospheres, making them prominent X-ray sources. Observations provide clues about the effects of disks of gas and dust around protostars. These disks evidently cause bipolar flows that push into the surrounding ISM and produce glowing nebulae called Habering Oreo objects. Astronomers also have abundant evidence that these disks are the sites of planet formation. So in some cases, the dark disks of gas and dust are clearly visible around newborn stars. So here we can see a star forming is hidden inside its cocoon, but we have these jets going out due to the angular momentum. The detection of these jets was one of the first pieces of evidence that substantial disks often surround protostars. Some evidence of stellar youth is more subtle. An association is a widely disturbed star cluster that is not held together by its own gravity. Its stars wander away as the association ages. The constellation Orion, a known region of star formation, is filled with T Tauri stars in a T association. T Tauri stars are approximately low-mass main sequence objects. OB associations, fairly obviously, are extended groups of more massive O and B stars. Associations of stars are journeying away from each other as we watch are clear evidence of recent star formation. So how would you go about making a star? It's simple, really. All you need is something to gather together a star's mass of interstellar medium, maybe a light year-sized broom, and gravity will do the rest, contracting the cloud first into a protostar and then into a stable star. The structure of a star is surprisingly simple. So the next question we need to answer is, what keeps a star stable? If there is a single idea in stellar astronomy that can be called crucial, it is the concept of balance. Stars are held together by their own gravity, balanced by the support of their internal heat and pressure. This is quite important. So I usually like to ask this question as a method test and exam, is what keeps a star stable? And that is their own gravity, balanced by the support of their internal heat and pressure. So keep note of that. So consider the structure of a star. Using the basic concept of balance, what is meant here by the structure is the variation in properties such as temperature, density, pressure, and composition between the surface of the star and its center. You can think more easily about stellar structure if you imagine that a star is divided into many concise shells, like those in an onion. You can then focus on the temperature, pressure, and density in each shell. These helpful shells exist only in the imagination. Stars do not actually have such separable layers. So the weight of each layer in a star must be supported by the layers below, so closer to the center. So picture a pyramid of people in a circus stunt. The people in the top row do not have to hold up anyone else, and the people in the next row down are holding the people in top row, and so on. In a star that is stable, the deeper layers must support the weight of all the layers above. The inside of a star is made up of gas, so the weight pressing down on a layer must be balanced by the gas pressure in that layer. If the pressure is too low, the weight from above will compress and push down the layer. And if the pressure is too high, the layer will expand and lift the layers above. So this stable balance between weight and pressure is called the principle of hydrostatic equilibrium. So this is how it works. So we have the principle of hydrostatic equilibrium says the pressure in each layer of a star must balance the weight on the layer above. So consequently, the weight increases from the surface of a star to its center, and therefore the pressure must also increase. Everybody happy with that concept? Awesome. So now we need to talk about how energy transportation happens inside a star. So the surface of a star radiates light and heat into space and would quickly cool if that energy were not replaced. Because the inside of the star is hotter than the surface, energy must flow outward to the surface, where it radiates away. This flow of energy through each shell determines its temperature, which, as you saw earlier, determines how much weight that shell can balance. The movement of energy from the inside to the surface of a star thus plays a crucial role in determining the star's structure. So the law of energy transport says that energy must flow from hot regions to cooler regions, either via conduction, convection, or radiation. Conduction is the most familiar form of heat flow. If you hold the bowl of a spoon in a candle flame, the handle of the spoon glows warmer as heat in the form of motion among the atoms of the spoon is conducted from atom to atom up the handle. So this is a good visualization with conduction being with the heat this part of the spoon will feed the heat in the handle. Radiation, if you are sitting next to a fire, you are feeling the heat of the fire. And then convection, warm air rises up above a candle flame and cool air sinks. So the transport of energy by radiation is another familiar experience. Put your hand near a candle flame and you can feel the heat. What you actually feel are infrared photons, so packets of energy radiated by the flames and absorbed by your hand. So radiation is the principal means of energy transport in the interiors of most stars. Photons are absorbed and re-emitted in random directions repeatedly as energy works its way from the hot interior towards the cooler surface. The flow of energy by radiation is controlled by the opacity of the gas, its resistance to movement. Opacity in turn depends strongly on temperature. A hot gas is more transparent, less opaque than a cool gas. If the opacity is high, radiation cannot flow through the gas easily, and it backs up like water behind a dam. When enough heat builds up, the gas begins to churn as hot gas rises upward and cool gas sinks downward. This heat-driven circulation of a fluid is called convection that we already discussed in an earlier lecture. And the third way energy can move inside a star. So you are familiar with convection. The rising wisp of smoke above a candle flame is carried up by convection. So there is a common misconception that a sun's core is hot because nuclear reactions occur there. That statement reverses cause and effect. Rather, it is correct to say the sun and other stars have nuclear reactions in their cores because the temperature is hot enough there. You observe the sun to be stable, therefore it must have a certain temperature, pressure, and density in its core. If somehow you could magically turn off the nuclear reactions in its core, then without a source of energy to replace the luminosity of pouring out into space, the sun would gradually lose its internal energy and start slowly contracting again, as was true during its protostellar phase before the nuclear reactions started. So now we need to talk about the CNO cycle. So you might expect other stars to fuse hydrogen the same way the sun does. And you would be right for most stars. But some stars, however, fuse hydrogen by another process. And that makes a big difference in their structures. So when we look at figure 9.15 and study the steps in a CNO cycle, during the process, 4 protons combine to make helium nucleus. In other words, the CNO cycle is really hydrogen fusion and has the same outcome as the proton-proton chain. But it is different in important ways. So notice that carbon-12 begins the cycle and ends the cycle. So the carbon-12 nucleus is recycled over and over. So notice also that a CNO cycle includes steps in which protons, so that means hydrogen nuclei, combine with carbon. So the CNO cycle in this image shows carbon-12 as a catalyst to combine 4 hydrogen nuclei to make 1 helium nucleus plus energy. And the carbon nucleus reappears at the end of the process, ready to start the cycle all over. But that happens in some stars, but a normal will just be proton-proton fusion. So newborn stars contract and heat up until nuclear fusion begins. The energy flowing outward from the core heats the layers of gas, raises the pressure, and stops the contraction. This leads to an interesting question. How does the star manage to make just enough energy to stop contracting, but not to start expanding? The key is the relationship between pressure and temperature that acts like a thermostat to keep the star burning steadily. Consider what would happen if the reactions begin to produce too much energy. Normally, the nuclear reactions generate just enough energy to balance the inward pull of gravity. If the star makes slightly too much energy, the extra energy flowing out of the star would force its layers to expand slightly, lowering the central temperature and density and slowing the nuclear reactions until the star regains stability. The star has a built-in regulator, the pressure-temperature thermostat, that keeps its nuclear reactions from occurring too rapidly. So now we can put what we learned together into a stellar model. So the laws of stellar structures described in general terms in the previous sections can be written as mathematical equations. By solving those equations, astronomers can build a mathematical model of the inside of a star. If you wanted to build a high-quality model of a star, you would have to divide a star into about 100 concentric shells, and then write down the 4 equations of stellar structure for each shell. So you would then have 400 equations that would have 400 unknowns, namely the temperature, density, mass, and energy flow in each shell. So solving 400 equations simultaneously is not easy. And the first such solutions done by hand before the invention of the electronic computer took months of work. Now a properly programmed computer can solve these equations in a few seconds and print a table of numbers that represents the conditions in each shell of a star. And such a table is a stellar model, a mathematical description of the inside of a star. So this is the different formulas, our 4 different equations, and this is the table it will produce. So when a contracting protostar begins to fuse hydrogen, it stops contracting and becomes a stable main sequence star. The most massive stars are so hot that they light up the remaining nearby gas in a beautiful nebulae, as if announcing their birth. After the gas of the nebula disperses, the star begins its long, mostly uneventful life as a main sequence star. In a careful consensus of all stars, including white dwarfs, about 80% are main sequence stars. Observations of the temperature and luminosities of stars show that main sequence stars obey a simple rule. The more massive a star is, the more luminous it is. That rule, the mass-luminosity relation, is the consequence of the mechanisms causing the stability of main sequence stars. In fact, the mass-luminosity relation is predicted by theories of stellar structure, giving astronomers direct observational confirmation of those theories. To understand the mass-luminosity relation, recall firstly the principle of hydrostatic equilibrium, which says that pressure balances weight. And secondly, the pressure-temperature thermostat, which regulates energy production. A star that is more massive than the Sun has more weight pressing down on its interior. So the interior must have a higher pressure to balance that weight. And that means the massive star's automatic pressure-temperature thermostat must keep the gas in its interior hot and the pressure high. A star less massive question. Sir, didn't you say that the white dwarfs, it's not always the case that more dense means more luminous, or am I misremembering? So that depends on what we're talking about. So yes, the more dense you are, and generally the more luminous you are as well. But that density depends on how much mass you started off when you started. So remember, when you have a low mass star, at the end it will end up as a white dwarf that is very dense. So it depends on what is the object we are talking about. So the mass-luminosity relation tells you why the main sequence must have a lower end. Low mass objects have lower pressures and temperatures in their cores, and those with less than about 0.08 solar mass are too cool to allow hydrogen fusion, called brown dwarfs. Such objects have diameters only about the size of Jupiter, so 10 times the size of Earth. And although they are still warm from contraction, they do not generate energy. So here we can see a small star and a brown dwarf and a gas giant. So that is where we define the lower limit. So the lower limit is a brown dwarf. So a brown dwarf doesn't have enough mass and pressure to start hydrogen fusion, but it's still warm from contraction. So if you compare a brown dwarf to a gas giant such as Jupiter, it's not too far off. So sometimes it is joked and said that Jupiter is an overachieving planet or underperforming star. So that's just a bit of a joke, but that is how we distinguish them from each other and where we draw the line of what is a star and what is a dwarf star. So brown dwarfs fall in a gap between low-mass M stars and massive planets like Jupiter. In the form of new stellar spectral types cooler than them, the warmer brown dwarfs fall in spectral class L and the cooler in spectral class T. Brown dwarfs would look dull reddish orange to your eyes, hence the term brown, but emit most of their energy in the infrared. Brown dwarfs are so cool that liquid and solid particles of silicates, metals, and other minerals can condense to form cloud layers in their atmospheres. Evidently, brown dwarfs have rocks for weather. A star in a main sequence is stable with its gravity balanced by outflowing energy from fusing hydrogen. The balance must shift as the star consumes its fuel, so that even apparently stable main sequence stars have interiors that are slowly changing. As a main sequence star fuses this hydrogen, 4 hydrogen nuclei are converted into a single helium nuclei, and the total number of particles in its interior decreases. Each newly made helium nucleus exerts the same pressure as one hydrogen nucleus. But because the gas has fewer nuclei, its total pressure is less. This unbalances the gravity pressure stability, and gravity squeezes the core of the star more tightly. As the core slowly contracts, its temperature increases and a nuclear reaction runs faster, releasing more energy. This additional energy flowing outward forces the outer layers to expand. As the star becomes gradually larger, it becomes more luminous, and eventually the expansion begins to cool the surface. As a result of these gradual changes in main sequence stars, the main sequence is not a sharp line across the HR diagram, but rather a band. Stars begin their stable lives fusing hydrogen in the lower edge of this band, which is known as the zero-age main sequence. But gradual changes in luminosity and surface temperature move the stars upward and slightly to the right. By the time they reach the upper edge of the main sequence, they have exhausted nearly all the hydrogen in their centers. Thus, you find main sequence stars positioned throughout the band at various stages of their main sequence lives. So in this image, we can see a newborn star reaches stability with properties that placed on an HR diagram at the lower edge of the main sequence band, along the line called the zero-age main sequence. As a star converts hydrogen in its core to helium, it changes slowly from a ZAMS and across the main sequence, becoming slightly more luminous and cooler. Once a star consumes all of its hydrogen at its core, it can no longer remain a stable main sequence star. So more massive stars age rapidly, but less massive stars use up the hydrogen they cause more slowly, and live longer main sequence lives. The Sun is a typical main sequence star. As it undergoes these gradual changes, Earth will suffer. So when the Sun began its main sequence life almost 5 billion years ago, it was only about 70% as luminous as it is now. And by the time it leaves the main sequence in another 6 billion years, the Sun will have twice its present luminosity. Long before that, the rising luminosity of the Sun will drastically modify Earth's climate and ultimately boil our oceans away. And life on Earth will probably not survive these changes in the Sun, but we have 1 billion years or more to prepare for it. So this you can go through on your own. It's just a spectral type, how much mass it has, and how its luminosity is, and how many years it spends on the main sequence. So here is a reasoning with numbers. This is another example I can ask for this semester as an exam. So you can estimate the amount of time a star spends on a main sequence, its life expectancy denoted by tau, uppercase tau, by estimating the amount of fuel it has, dividing by the rate at which it consumes the fuel. So tau equals the fuel supply divided by the rate of consumption. So the amount of fuel a star has is proportional to its mass m, and the rate at which it uses its fuel is proportional to its luminosity L. So this, if a life expectancy must be proportional to m divided by L, so mass divided by luminosity. So you can simplify this equation further, as you saw in reasoning with numbers 8.5, when luminosity of a star depends on its mass raised to the power 3.5. So we can substitute that into the equation. That means tau equals mass divided by mass to the power 3.5. So we can simplify that further by saying tau equals 1 divided by mass to the power 2.5. And if you express the mass in solar masses, the lifetime will be in solar lifetimes. So example, how long can a 4 solar mass star live? So you just take that equation, we plug in 4. So solar mass, and that gives us 1/32 solar lifetimes. So solar models showed that a sun presently 5 billion years old will last another 6 billion years. This solar is approximately 11 billion years, and a 4 solar mass star will last for about 340 times 10 to the power 6 years. So ladies and gentlemen, do you have any questions? Any questions? So we still have time left and therefore have to continue with our next set of lecture slides. So I'm just uploading the next set. So for the calculations we have to do, we'll be getting a formula sheet. Yes, you will get a formula sheet with all the formulas and constants on. So you will just be able to need to understand how to use the equations. It's almost finished uploading. So now that we learned how a star is formed, and how stars are formed, what do you guys guess is the next thing we need to talk about? So we need to learn up to and including lecture 9. So you have to learn to where we end off in lecture 10. Yes, so Jean, you are correct. The next thing we now need to talk about is what happens when a star dies. When a star dies. So do you guys have any suggestions of what happens to a star when it dies? Yes, that's one of the things. So what we will learn is one of three things will happen to a star at the end of its life. Will the equations be labeled, or will we have to know when to apply which formula for given question? Yes, you will need to know when to apply which formula. I won't label the equations. So at the end of a star's life, depending on how big it is, if not big, how much mass it has, it will either end off as a white dwarf that we've briefly touched on, or as a neutron star, or as a black hole. But to understand what happens with each of them, we need to understand what happens to the death of giant stars, low main sequence stars, binary systems, and massive stars. So at the end of this lecture, we need to answer these questions. So what happens to a star when it uses up the last of the hydrogen in its core? Secondly, what evidence shows that stars really evolve? Thirdly, how will the sun die? Fourthly, what happens if an evolving star is in a binary system? And lastly, how do massive stars die? So let me ask you guys a question. So what happens when a star uses up all its hydrogen? Any ideas? So depending on the mass of the star, it will start fusing the next, not collapse yet. So if you have an average star such as an own sun, you will start fusing the next element. So when hydrogen fuses, it creates helium. So then you start with helium fusion, and if you still have enough mass, you can use helium fusion to carbon fusion. So our own sun will merely fuse helium into carbon, but our own sun doesn't have enough mass to fuse carbon into the next element. If you have even more mass, you can keep on fusing, but it doesn't matter how much mass a star has. You cannot fuse iron. Iron is a star killer, and we will talk about that in a later lecture. But in essence is, when you fuse iron, the fusion process makes use of more energy than it releases with iron, and that's why it is not stable. So why does helium fusion make carbon and not beryllium? So it depends on your atomic mass. So at first, if you look at the table of elements, let me see if I can quickly show that. So let me just try and get the table of elements. Oh, come on, just normal table of elements. Let's see if I can share my screen. Can everyone see my screen? So when we're speaking about fusing, we speak about stable elements, and carbon is more stable than the elements in front of it. So that is why carbon is the next element that will be fused. So if we go to that stability that we precisely look at, when we fuse hydrogen, the main product or the main element with the fusion process will be helium. And then when we fuse helium, we will get carbon, but some of the helium atoms, so even though hydrogen is used up, there will still be one or two hydrogen elements left. And that will create oxygen, but not a lot of oxygen. So that is, the majority will be carbon with a few trace elements of oxygen. That's where oxygen comes from. So then when we have carbon fusion, the main elements we'll be getting is neon and then a little bit of magnesium. And then when we fuse neon, then we get a lot of oxygen and a little bit of magnesium. And when we fuse oxygen, we get silicon and a little bit of sulfur. And once we fuse silicon, we get iron, and nothing can fuse after iron. So we look at the stability of the elements. Does that make sense? Awesome. So in class, this would have been a nice animation of the Death Star destroying Alderaan in Star Wars. But when we talk about a death of stars, it's not a Death Star in Star Wars or a star that just blows up. But this animation would show the star collapsing in on itself and blowing its outer layers outward. So deaths of stars are important because life on Earth depends on the sun, but also because the deaths of massive stars created the atomic elements of which you are made. If stars didn't die, you would not exist. So the only place in the universe where we can fuse elements heavier than iron is in supernova explosions. That is why I used the quote of Carl Sagan. The iron in your blood, the calcium in your teeth and bones, those are all made in supernova explosions. The death of big stars, the gold in our ground, the platinum is all made up of dying stars. So here we can see where these different elements are being made. So when we look at our normal yellow, we will get our yellow from merging neutron stars. So two neutron stars that collide with one another that we will talk about. The dark blue is just expanding massive stars. Light blue is exploding white dwarfs. The red was in the Big Bang. The orange ones is in the dying low mass stars, and the purple ones is in cosmic ray fission. So now you can see where your elements are being made. So depending on how much mass a star has, it will form in the stellar nebula. So one thing that we learn in a later lecture is, if a star has planets orbiting it and the planets has moons orbiting them, everything formed at the exact same time. The star, the planets, and the moons all formed at the exact same time. So when we have a star that's being born with its planets and moons, it will be an average star or a massive star. An average star will become a red giant. The red giant will blow off its outer layers, and we will have a planetary nebula with the naked core not fusing energy anymore, but it's just radiating energy. Once the nebula is blown away, we will just have a white dwarf. If we have a massive star, that will become a super red giant. With the super red giant, it will create a supernova explosion, and the core will collapse in on itself. And then, depending on how much mass it has, It will either form a neutron star or a black hole. And in this lecture, we will distinguish between the two and what is the point where a neutron star is made or when a black hole is made. Does anyone have any questions so far? So what is the yield of a supernova when it makes heavier elements? Like, does it make tons of, example, titanium, or does it only make a few grams? I imagine the mass of a star makes a difference. Yes, it makes a difference. So I'm not exactly sure of the yield, but it creates a whole lot of that specific element. So it's not only a few grams, but it actually creates in that explosion a couple of thousand tons, if I can put it that way. So gravity is patient, and stars generate tremendous energy resisting their own gravity. But no star has an infinite supply of fuel for its nuclear reactions. So when the fuel runs out, the stars die. So when it's fusing energy, we have gravity pulling the outer layers downward, and then we have the pressure pushing that upward. And that is our stability, our pressure temperature thermostat. But as soon as the star cannot create more energy and more pressure pushing outwards, then that collapses in on itself, and then what happens to the star depends on how much mass it has. So occasionally, astronomers see a formerly faint star suddenly appear much brighter in the sky, then fade away after a few weeks or months. And you will learn that what seemingly a new star in the sky is called either a nova, an eruption on the surface of a stellar remnant, or a supernova, the violent explosive death of an aging massive star. So if you recollect, in a couple of lectures ago, I said Betelgeuse, that is in Orion, is currently now being observed because its brightness almost doubled in a short period, and it's still increasing. So what that means is that's a strong indication that a star is about to go supernova. We don't know exactly when, but yes, that is an indication, and that's something cool to look out for. So a few novae, is plural of nova, are discovered each year, and supernovae, plural, are so rare that only one or two occur each century in our entire galaxy. But astronomers surveying thousands of galaxies scan many supernovae flare per year. The mass of a star is critical in determining its fate. Massive stars can die in violent supernova explosions, but lower mass stars die quiet deaths. To follow the evolution of stars to their graves, you can start by following the life story of a sun-like medium mass star as it becomes a giant star. After that, you will learn how stars of different masses end their lives. So massive red supergiant star V838 flared up in 2002, and the expanding shell of light from the flare illuminated surrounding gas and dust that was probably ejected from the star in earlier outbursts. And bright spikes are produced by the diffraction in telescopes. Planetary nebula IC1295 consists of shells of gas expelled by an aging red giant star. The star remnant can be seen in the center of the nebula, contracting to become a white dwarf. An intense UV radiation from the central star is making the nebula glow, and the prominent green color is emissions from ionized oxygen. And Plan A, near infrared image of galaxy M82, so Messier 82, and supernova 2018J observed from the Stratospheric Observatory for Infrared Astronomy, SOFIA. And the other two labeled objects are foreground stars in our galaxy. A giant main sequence star generates its energy by nuclear fusion reactions that combine hydrogen to make helium. The period during which the star fuses hydrogen lasts a long time, and the star remains on the main sequence for 90% of its total existence as an energy-generating star. And when the hydrogen is exhausted, however, the stars begin to evolve rapidly. The nuclear reactions in a main sequence star cause fused hydrogen to produce helium. Because main sequence stellar cores are cooler than 100 million Kelvin, the helium can't overcome the Coulomb barrier to fuse in nuclear reactions. So it accumulates at a star center like ashes in a fireplace. Initially, the helium ash has little effect on the star. But as hydrogen is exhausted and the stellar core becomes almost pure helium, the star loses the ability to generate nuclear energy that opposes gravity. And as soon as the energy generation starts to die down, gravity begins making the core contract. What is the Coulomb barrier? Let's see if I can explain that in an easy way. So the easy way to explain the Coulomb barrier is, so if you played with magnets, what happens if you have magnets with the same charge near each other? So for example, two positively charged magnets or two negatively charged magnets. Yes, they push each other away, exactly. So the Coulomb barrier is, in essence, the same thing. So we call that electrostatic repulsion. So when we have two positively charged nuclei and they come close to one another, they must overcome this electrostatic repulsion to get close enough for the strong nuclear force to bind them together and initiate nuclear fusion. And that's the repulsion strength, or that repulsion, is what we call the Coulomb barrier. Does that answer your question? Awesome. So although the core of helium can't generate nuclear energy, it does grow hotter as it contracts because it is converting gravitational energy into thermal energy. And the rising temperature heats the unprocessed hydrogen just outside the core. And hydrogen that was never before hot enough to fuse, soon hydrogen fusion begins in a spherical layer or shell around the exhausted core of the star. Like a grass fire burning outward from an exhausted campfire, hydrogen fusion shell creeps outward, leaving the helium ash behind and increasing the mass of the helium core. So what that in essence means is, when our own sun, it fuses hydrogen into helium, the helium cannot start to fuse yet. So what happens is, all the hydrogen first needs to be fused into helium. So once all the hydrogen is fused into helium, helium has a bit more mass, so then the reactions die down and the helium pushes down on the core. So when you push down on the core starts to contract. And when a core starts to contract, due to the gravity, it starts to heat up again. Then it heats up so much you now have enough heat to have helium to start fuse. So now we call the helium that created the helium ash. So the helium now starts to fuse into carbon. So now the star continues on its way and happily fuses helium. So when helium fuses, it creates carbon. So a carbon shell is formed around the star. So the carbon cannot start to fuse at a moment. So we start a process from scratch again. So once all the helium has fused, the carbon starts pushing down on the core starts to contract, and if it becomes hot enough, then you can start fusing carbon again. But if it cannot become hot enough, then that is where the star will die. So then the outer layers are pushed away, and it creates a white dwarf. So here we can see the flood of energy produced by the energy fusion shell pushes towards the surface, heating the outer layers of the star and forcing them to expand dramatically. Stars like the Sun become giant stars of about 10 to 100 solar radii, and the most massive stars become supergiants some 1,000 times larger than the Sun. And this explains the large diameters and low densities of the giant and supergiant stars. The expansion of its envelope dramatically changes a star's location on the HR diagram. Just as contraction heats a star, expansion cools it. As the outer layers of gas expand, energy is absorbed in lifting and expanding the gas. The loss of that energy lowers the temperature of gas. Consequently, the point that represents the star in HR diagram moves to the right relatively quickly, in less than 1,000,000 years for a star of 5 solar masses. A massive star moves to the right across the top of the HR diagram and becomes a supergiant, while a medium mass star like the Sun becomes a red giant. So here we have it with the expansion. So a 15 mass star, like Betelgeuse, will become a white supergiant and then a red supergiant. 5 solar mass star will become a red giant. Yeah, 3 solar mass become a red giant, and our Sun will become a red giant. So as the radius of our giant star continues to increase, its enlarging surface area makes the star more luminous, moving its point upward in the HR diagram. The famous star Aldebaran, the glowing red eye of Taurus the Bull, it's such a red giant with a diameter more than 40 times that of the Sun, but a much cooler surface temperature. So when we look at Orion in the night sky, if you look at Orion's belt, the red star that's over here, that is Aldebaran. And Aldebaran also usually points towards Pleiades. So that is Aldebaran if you look through a telescope. So the next thing we talk about is degenerate matter. So although the hydrogen fusion shell can force the envelope of a star to expand, it can't stop the contraction of the helium core because the core is not hot enough to fuse helium. Gravity squeezes it tighter and it becomes very small. When a gas is compressed to such high densities, it begins to behave in surprising ways that can affect the evolution of a star. To continue the story of stellar evolution, you need to consider the behavior of a gas at extremely high densities. Normally, the pressure in a gas depends on its temperature, and the hotter a gas is, the faster a particle moves, and the more pressure it exerts. The gas inside a star is ionized, so there are two kinds of particles, atomic nuclei and free electrons. Under normal conditions, the gas in the star follows the same laws relating pressure and temperature as gases do on Earth. But if the gas is just one of two possible directions, two electrons can occupy a single energy level only if they spin in opposite directions. That level is then completely filled, and the third electron can't enter because whichever way it spins will be identical to one of the other of the two electrons already in the level. A low-density gas has fewer electrons per cubic centimeter, so there are plenty of energy levels available if a gas becomes very dense. However, nearly all of the lower energy levels are occupied. In such a gas, a moving electron can't slow down. Slowing down would decrease its energy, and there are no open energy levels for it to drop down to. It can speed up only if it can absorb enough energy to leap to the top of the energy ladder, where there are empty energy levels. So here we can see our valence orbits or energy levels in a low density gas and in a high density gas where these two electrons spin in opposite directions. So when a gas is so dense that electrons are not free to change their energy, astronomers call it degenerate matter. So this is a definition that is very important. Although it is a gas, it has two peculiar properties that can affect the star. First, the degenerate gas resists compression. To compress the gas requires pushing against the moving electrons, and changing their motion means changing their energy. That requires tremendous effort because you must boost them to the top of the energy ladder. That is why degenerate matter, still a gas, is harder to compress than the toughest hardened steel. Second, the pressure of degenerate gas does not depend on temperature. So usually pressure depends on temperature, but not for a degenerate gas. And to see why, note that the pressure depends on the speed of the electron without tremendous effort. The temperature, however, depends on the motion of all the particles in the gas, and both electrons and nuclei. So if you add heat to the gas, most of the energy goes to speed up the motions of the nuclei, which move slowly and don't contribute much to the pressure. Only a few electrons can absorb energy to reach the empty energy levels at the top of the energy ladder. This means that changing the temperature of the gas has almost no effect on the pressure. These two properties of degenerate matter become important when stars end the main sequence live. Eventually, many stars collapse into white dwarfs, and you will discover that these stars are made of degenerate matter. But long before that, the cores of many giant stars become so dense that they are degenerate, a situation that can produce a cosmic bomb. So what that means is when we start fusing elements, so when we have all our hydrogen fused and it creates helium. The helium is a form of degenerate matter. So now you have the helium pushing downwards, we have contraction from the stars, and that contraction causes your helium to fuse into carbon, and you overcome the degenerate matter, but then the carbon becomes degenerate matter. And that continues on until you reach the end. So what is interesting is how much mass you have left. If you can compress the degenerate matter even further, you can create a neutron star. And if you can compress it even more, then you can create a black hole. So ladies and gentlemen, I think we are going to end the lecture right here. So the semester test will be everything up until this slide. Do you have any questions? So will the memo of the semester test memo be posted or not? Yes, I'll post a memo after the semester test. I've also, so what is dark matter? So we will learn about dark matter, I'll talk about it in a later chapter, but currently the best answer is we don't know what dark matter is. So you will also have noticed I've uploaded a mock semester test and mock exam. You can use that as practice and to see how I will be asking questions. So remember, this Saturday afternoon will be our recap class. I will go through the memo of the mock semester test in Saturday's recap class. So question, are the only the slides sufficient material to study? It's dependent on what your study material is. My slides are very thorough, so you should be doing, it will be, so depending on how you study, I would use the textbooks and slides, but the slides are quite thorough, so you should be okay, but it all depends on your lecturing or your learning style. So how should we understand the Balmer H series as well as the other series? So the Balmer, I won't ask anything directly about the Balmer H series or the Balmer hydrogen series. So I think you already answered this question, but do we get the formula sheet? We'll be only given the formula when we need it for a particular question. I will give you a formula sheet. It's a pleasure. So I will remain active for another minute or two. So sir, can you please maybe quickly recap on the degenerate matter and its properties? So with degenerate matter is, let's go to this slide. So when we have a low density gas, it means we have a lot of open are the definitions that we will have to know, sir. So through all the lectures I will give you, I won't ask a definition exactly as it is. Just need to explain what something is. So for example, if I ask you what is degenerate matter, just describe what degenerate matter is and don't list the definition like something that's been regurgitated as a parrot. Just know it. So for example, the degenerate matter, when you have a low density gas, you will see most of its energy levels, or we can call it valence orbits, are open, and there's not an electron on each energy level or each valence orbit. So usually in each orbit or energy level, we can have two electrons that spins in opposite directions. So if you compress a gas, making it a high density gas, then you start filling up these energy levels with two electrons. So the only way you can add more electrons to it is if you add enough energy that those electrons can go to the higher energy levels. But if you have a situation where all your energy levels are full, that is degenerate material or a degenerate gas or a degenerate element. And the only way that we learn is temperature in a degenerate material doesn't make a difference. The only way you can add more electrons to it is if you increase the pressure in some way. And to increase the pressure, we will learn is to add more mass. And that is what degenerate matter is. So that answers the question. Pleasure. So in last week's class, we voted on it. So the recap class will be this Saturday afternoon from 3 to 4. It's a pleasure. So if you guys have no further questions, you're more than welcome to log off. Otherwise, I will still remain active for another minute or two. So otherwise, thank you for a great lecture, and I will see you all in Saturday's recap class. I will check what venue is and make an announcement. Our recap class will be online. Will our noble gases be an example of degenerate matter? Sort of, yes. So here when you speak about degenerate matter can apply to all elements. And now, Ray, so the recap class will be online this Saturday. So question, so you could have carbon, and as long as all the valence shells are filled, it would be a degenerate matter. Yes, that is correct. It is a pleasure. So I see there's no further questions, so I'm also going to log off. So have a wonderful evening and enjoy the rest of your week.